Hello, everybody, and welcome to another wonderful day of physical chemistry. So today we're going to be expanding on our previous conversation about electronic spectra by focusing in on our fine structure. So this is mostly going to be how vibrational excitations can couple with electronic excitations. So one of the first things to realize about electronic excitations is that if I'm going to change the electronic structure of a molecule, one of the things that's typically going to result is a change of the entire potential energy surface. So one of the ways you can think about this, as I do perform an electronic excitation, we're often going to change the bond order of the molecule. We're going to excite from a bonding to an antibonding orbital, most likely. Well, as a result, oftentimes our equilibrium bond length is going to change. And so we're going to see some sort of change in the shape and location of our potential energy well. Most typically, it's going to end up moving towards a longer equilibrium distance, and the well is going to become much shallower as the system will be less firmly bound. Now, as a result, this is going to cause a change in the vibrational state because as soon as my potential well changes, this is going to change such things as the vibrational constant as well as the well depth. This is going to have a lot of important consequences on how my molecule moves in this new electronically excited state. Now, trying to um, trying to explain this new set of movement can actually be quite difficult. So we can fall back on one of our old tools, the Born-Oppenheimer approximation. Mostly, this is the idea that electrons move much faster than nuclei. And because of this, we can frame this in a new principle called the Frank-Condon principle, which essentially is a specialized case of the Born-Oppenheimer approximation. So the idea is that nuclei, much more massive than an electron, much slower moving. So any electronic excitation is going to occur very rapidly. And then the nuclei are going to have to respond to that electronic excitation much more slowly. In principle, what we often do is we treat the nuclei as being static to any sort of electronic change. So the nuclei ain't going to move nearly on the same time scale as an electron. So as a result, we are expecting molecules to undergo vertical transitions for electronic excitations. So again, nuclei stay put, system goes up to the new electronically excited potential well. Now, if I've got if both of my potential wells have the same equilibrium bond length, this is going to be an easy solution. Just move straight from one to the other. However, if the potential wells differ, especially in terms of equilibrium bond length, this means that I'm going to move towards an excited state because my energy isn't going to be at the ground state. It's going to be somewhere higher up. So we can repeat this idea, except for bringing in some of our quantum mechanical principles. Specifically, we're going to be focusing in on wave functions and overlaps. So we're going to expect the excitation with the highest probability is going to be the one where the electronic and the vibrational ground states are the most similar. Specifically in this case, where their vibrational wave functions are the most similar. So this is going to be fairly straightforward again if the equilibrium bond length is same for both cases, because if I excite out of the vibrational ground state, which we're going to represent as V double prime, we'd expect to excite into the into the vibrational ground state for the excited electronic state, which we're going to represent as V prime equals 0. So double prime for electronic ground, single prime for electronic excited. So we'd expect to go from ground to ground because they both have the highest vibrational intensity around that equilibrium bond length. However, and this should be the most, again, common transition. However, most of the time, we're going to expect that equilibrium bond length to move. Again, we typically would expect to excite an electron from a bonding orbital to an anti-bonding orbital, which should decrease the bond order, increasing bond length. Now, if this happens, we'd expect the system to have the best overlap with a wave function which has a high intensity near the walls. Well, it turns out that this is going to be the most common for a vibrational excited state because you'll notice the ground state has no intensity out there. And one of the reasons why this is going to happen most commonly with an excited state is because not only does it exist out at these shorter bond distances, but if you remember back to our vibrational systems, they tend to have the highest intensity near the walls. So it's going to have a high intensity at short and a high intensity at long distances. So we're going to have the best overlap in between my ground state wave function and my excited state wave function when we're dealing with vibrationally excited states, especially when we're seeing this lengthening of the bond. So because these vibrational excited states are most likely to have short bond distances, we're going to see the largest extent of overlap. And we can, again, try and model this idea of the probability of a transition using our good old friend, the transition dipole moment operator, to, again, find the overlap in between the initial and the final wave function, where we're going to specifically be looking at the probability of the initial to final transition. So we're going to do this by breaking our wave function and our operator down into its electronic and nuclear components. So the nuclear is going to be with the trailing element of the nuclear movement, and the electronic is the excitation we're mostly going to be looking at. And as we can do this for my wave function, I can also do it for the operator, where I'm going to have an electronic and a nuclear excitation. Now let's go ahead and apply the system. So using bracket notation, I can insert all the operators, subdivide my wave functions. First thing I'm going to want to do is to FOIL it out and simplify. So doing this, I can have split it out to the part of this, and using orthonormality, I can split out to the part of the system where I'm exciting the electronic part of the system and the nuclear part of the system. Now, one of the first things that's important to realize is we're going to be looking at an electronic transition. So we know that my initial and final wave functions have to be orthonormal to each other. So any overlap in between different initial and final structures, as we're going to have for an excitation, are going to be different. Thus, this overlap will be 0. So this whole second part of the equation just drops out of the picture. Now, note that this restriction is relaxed if we were going to try and apply the same principle to, say, rotational or vibrational movement, at which point most of the excitation is happening in the nuclear component and the electronic state is not changing. So we are then left with the remaining terms. So it turns out that our electronic selection rules are going to control this first part of the equation. So these are the ones we talked about previously, whether the reaction is spin allowed, spin forbidden, parity allowed, parity forbidden, or whether it's allowed by angular momentum. All of that is going to be embodied in this first part. This leaves us with the last part. So this is going to be our nuclear overlap. It's how much my nuclear wave functions are going to interact. And so this is going to be related to the overlap of the nuclear wave functions. And this is really what's going to help control signal intensity. So in practice, what we're going to be using is a vibrational wave function instead of a nuclear wave function, because remember, the vibrational wave function should represent the nuclear motion. So it's a pretty good trade in here. And then we can use this vibrational wave function to calculate what's called a Frank-Condon factor. And this is more or less the squared of the overlap in between these two wave functions. So the transition intensity, or how intense the signal is going to be related to the square of my overlap, which we can then do by more or less just taking the integral of the system. So in practice, we can use ideas like this Frank-Condon factor to estimate transitions in between two wave functions. such as, for example, I've got two wave functions, one more wide, one more narrow. So we can estimate the Frank-Condon factor more or less by looking at the overlap region. So in this case, it's going to be represented by essentially how wide is my new overlap region compared to my original net wave function. If these two perfectly overlap, my Frank-Condon factor should be 1. If there's no overlap, it's 0. So it's going to be looking at these ratios of wave functions, really controlling my signal intensity. Now, it is worth remembering that this still won't be the only thing controlling signal intensity, as all of my selection rules will still play a significant role. So let's go ahead and look at a quick example of this Frank-Condon factor for a real set of vibrational wave functions. So simplest system, if we were going to try and find a good vibrational wave function, is going to be the ground states. So we're going to go ahead and look at the excitation in between two vibrational ground states. We're going to try and excite from a electronic ground state to a vibrational excited state, here given by sigma prime. You'll notice that since they're both looking at the vibrational ground states, even if the electronic states are changing, they will have the same functional form, same normalization constant, same exponential decay. Only difference here is going to be this x term. So in this case, x is going to be the difference in between the location of the nuclei and the equilibrium bond length. So we'll have a ground state equilibrium bond length and an excited state equilibrium bond length. I can then go ahead and insert this x equation into both of these functions and then try and integrate the overlap. So my normalization constant should be able to move back forward. And then all I'm left with is these two exponential terms. However, since they're two exponential terms, I can merge and then have fun with quadratics as I have to combine them and look for elimination. And then don't forget, I'm then going to have to perform a integral over a Gaussian. So we're not going to be so interested in mathematical details, but it's worth noting you can simplify the answer into a simple exponential form. And it is worth noting that this means that my Frank-Condon factor is going to have an exponential decay. So using the overlap, we can then square the function, which turns the 4 in the denominator to a 2 to produce a Frank-Condon factor. So this is going to be proportional to my signal intensity. And one of the important things that we're going to see here is that my Frank-Condon factor and thus signal intensity is going to decrease as my two equilibrium bond lengths get further and further apart. Now, it is worth noting this is only for the 0 to 0 transition, but it does help indicate an important feature. The more my two wave functions differ, which is going to largely be driven by the difference in equilibrium bond lengths, the less likely I am to see a transition. And this is going to work through an exponential decay. So small differences of bond lengths won't make a big difference. But past a certain point, it's going to drop off, so I'll see very little signal. So this is where you'll often hear the term that it's going to be forbidden by Frank-Condon forbidden. And this is one of the important things to note is that this equational form of the Frank-Condon factor is going to depend whether I'm exciting from 0 to 0, 0 to 1, 0 to 2, 0 to 3. But it is possible to derive analytical forms of each of these Frank-Condon factors through a little bit of some tedious calculus. However, this gives us one of our first major controls over signal intensity. And we're going to spend a little bit more time next time diving into this idea of signal intensity and shape of our spectroscopic signals. Until then, take care.